Hi everyone, today we're going to talk about Gibbs Free Energy. This is tied to Learning Objective 5.13 that the student is able to predict whether or not a physical or chemical process that's thermodynamically favorable by determining the signs of the entropy change and enthalpy change and the calculation of Gibbs Free Energy change when needed. Willard Gibbs, he proposed a state function called G, the Gibbs Free Energy, that ties together enthalpy and entropy to determine if a process is thermodynamically favorable or spontaneous. Under standard conditions, which means 1 atmospheric pressure for gas, 1 molar for solutions or pure solid, pure liquid, delta G naught equal to delta H naught minus T delta S naught. Now this little naught circle meaning at standard state. That means the change in Gibbs free energy is equal to the change in enthalpy minus temperature in Kelvin times change in entropy. But one must remember that even if the process is thermodynamically favorable, it does not mean that it will proceed at a measurable rate. Remember, we cannot predict kinetics using Gibbs free energy. If the sign of delta G is less than 0, that means the products are favored at equilibrium, meaning equilibrium constant is greater than 1, forward reaction is favored. If the delta G equal to 0, the change in Gibbs free energy, reaction is at equilibrium. If delta G is greater than 0, reactants are favored at equilibrium, equilibrium constant is less than 1, the reverse reaction is thermodynamically favored. Now let's look at the diagram very carefully. Here we have the making of ammonia from nitrogen and hydrogen. Gibbs free energy versus time. And you can see that on the left-hand side of the diagram, we have too much of the reactant nitrogen and hydrogen. Equilibrium lies far to the right, meaning quotients less than K, then the forward reaction will be spontaneous to make more ammonia. So the Gibbs free energy will decrease from left down toward the middle. If you look at the right-hand side of the diagram, that means we have too much of ammonia, the product present, meaning quotient greater than K, equilibrium lies far to the right. That means ammonia will then decompose to form nitrogen and hydrogen in order to reach equilibrium. So the Gibbs free energy will decrease towards the center. Therefore, interpreting this diagram, we understand that Gibbs free energy decreases in the direction of spontaneous change. The left-hand side meaning spontaneous in the forward direction, the right-hand side meaning spontaneous in the reverse direction. We are now going to look at the effect of enthalpy change delta H, the entropy change delta S, and temperature on spontaneity. Basically, there are 4 cases that we will examine. In case number 1, when the reaction is exothermic, delta H is negative, and the system is becoming more random, the delta S is positive. Relating back to the equation, delta G is equal to delta H minus T delta S. Now, if the delta H is negative and the delta S is positive, the overall delta G will be negative. That means the reaction is thermodynamically favorable at all temperatures. An example of this will be the 2 moles of dinitrogen monoxide gas to become 2 moles of nitrogen gas and 1 mole of oxygen gas. And this reaction is thermodynamically favorable at all temperature, as the enthalpy is negative and the entropy is positive. In case number 3, where it is exothermic reaction, delta H negative, the system becoming more orderly, delta S also negative. When you put it into this Gibbs free energy equation, the delta G can be positive or negative depending on the temperature. Now, at low temperature, that means this negative T times negative delta S will be a small positive. The delta G will then be a negative because the enthalpy is negative. That means it is thermodynamically favored at low temperature. However, when temperature is high, then this negative T delta S will be increasingly positive to the extent that it can override the negative delta H and the delta G will become positive and therefore not favorable at high temperatures. Such as the freezing of water is favorable at 0 degrees but not at higher temperature. Case number 4, the last case. In an endothermic reaction where delta H is positive and the system becoming more random, so delta S also positive, when we plug these signs into the Gibbs free energy equation, the delta G can be positive or negative. Now that depends on temperature. If the temperature is high, the negative T delta S will be quite negative and the delta G will not end up to be negative. However, if the temperature is low, then this negative term, negative T delta S, will be quite small in magnitude, and the delta G could be positive and not favorable at low temperature. Hence, like the sublimation of dry ice from solid into gas, this is favorable at high temperature, but not at low temperature. So we should be able to utilize these 4 case scenarios to account for whether reaction will occur spontaneously or not. Practice problem number 1. In the combining of hydrogen and ethene to make ethane, the delta H is negative 137.5 kilojoule and the entropy change is negative 120.5 joule per Kelvin. Calculate delta G0 at room temperature and determine if the reaction is thermodynamically favorable or not. So now we plug it into the equation. One caution to students is that the entropy change is in a unit of joule, while the enthalpy change is in unit of kilojoule. So we must convert the entropy change into the same unit with enthalpy in kilojoule by dividing the entropy change by 1,000 before you add up, otherwise you get the wrong value. So the delta G0 is calculated as negative 101.6 kilojoule. The reaction, therefore, is thermodynamically favorable at room temperature. Now, what's the effect on delta G0 with increasing temperature? With increasing temperature, this T delta S0, this magnitude, will increase and the overall sign will become more positive or smaller negative. Therefore, this delta G0 will become smaller negative. I mean the negative T delta S will be more positive, larger positive, which will then decrease the delta G will become either a smaller negative or more positive. Continuing with that, at what temperature would the delta G0 change sign? At that time, this delta G0 will be 0, and therefore delta H0 is equal to T delta S0. So we can calculate the temperature at which the sign will switch. And this is equal to delta H0 in kilojoule divided by the delta S0. The delta S0 should also be in kilojoule. And the temperature is calculated as 1141 Kelvin or 868 degrees C. So the delta G0 will change sign from negative to positive when temperature reaches above 868 degrees C. So some of what we have learned today, we learned how to predict whether or not a physical or chemical process is thermodynamically favorable by determining the signs of the enthalpy change and the entropy change, and by calculating delta G0. I hope that you have found the above video helpful to you. If you like it, please give us a like, and I look forward to seeing you in the next part as a continuation of thermodynamics.